My name is Stephen Dang. Thank you for coming today. I am from Capital One, located in our locations in Dallas. I work in the auto finance sector, and we have a slew of tools that are architected for different levels of resiliency, and I've worked on a large number of them. So I've seen everything from internal tools that can be down for a week with no issues, maybe a mad email or two, and I've worked on projects that have that require to be up all the time, like our loan servicing, where we need to take customer data and take payments all day, every day, 24 hours a day. Hopefully you're here for architecting for active-active resiliency, and I'm gonna straight off the bat say, I say active-active very lightly. As you'll see, active-active is extremely complex, and there are many tiers of different resiliencies, and sometimes it's not always worth it to be completely active-active. So, what is resiliency right off the bat? Resiliency, we like to break down into two different levels. We have the data level and we have the service level. At the service level, you can look at resiliency as availability, where it's kind of the percentage of time your service is doing what it's supposed to do. And you can look at durability as how durable your data is, and whenever something goes down, what is your system's resilience to losing data, or your resistance to losing data. Now, your system or your system can be available but not durable. That's when your system accepts writes but doesn't necessarily commit the transactions. And it can also be durable and not available, where if your system can't make enough replicas of your data, then we're not going to accept writes. Today, we're going to kind of consider the trade-offs between raising the availability and durability, as well as the associated complexities with that. So, I don't know if everybody's seen this, but this is Waffles the dog, one of my favorite dogs that shows up whenever Amazon has a 404. I do think Waffles is one of the cutest dogs on there. So I'm picking on Amazon specifically for two reasons. The first reason is because I think Amazon has the cutest 404 page. And the second reason is because no matter how big or how small your company, you can have outages and you're going to have failures. And even a company, if you've heard of this small service called AWS, which Amazon hosts and provides, even they can have outages. So it's important to have a plan. So first off, we're going to talk about some of the basics. Then we're going to talk about considerations and trade-offs. We're going to talk about common patterns to increase your resiliency. And we're also going to talk about a couple tools and services that'll help you, and that'll be dispersed throughout the presentation. So first off is our ingredients. And I say ingredients because I really, really like food. So if you guys have dinner plans tonight that has delicious food, let me know. So we're going to talk about, first, availability. What is availability? In simple terms, your availability can be calculated by your normal operation time divided by your total time. In slightly more technical terms, your availability time is your mean time before failing, and your total time is your mean time before failures plus the time it takes to recover from those failures. Now, that's availability of your one system, but what happens when we have multiple systems? Obviously, not everything's going to be monolithic these days. We are venturing towards a very distributed world. Let's say we have component X and we have component Y, and component Y is a downstream dependency of component X. If component X has 2 nines of availability, that equates to about 3 days and 15 hours, give or take a leap year. If component Y has 4 nines of availability, we're going to have about 52 minutes of downtime per year. When you put them in series, where X is dependent on Y, your availability can be calculated via the product of those availabilities. And we're down to 98.99 availability. And our downtime per year is now 3 days, 16 hours, and 33 minutes. And if you've noticed, our new availability levels are lower than the other components individually. So what do we take away from this? More downstream dependencies, less availability. But what happens when we have something in parallel versus in series? Say we have 2 X's, or 1 X, and your availability is 99%. Again, that's 3 days and 15 hours per year. When you put 2 X's in parallel, your availability becomes 4 nines of availability. That's only 52 minutes per year. When you put 3 X's in parallel, you're down to a whopping 31 seconds. And that is huge. By putting 3 of your components in parallel, you're tremendously adding or reducing your increasing your availability and reducing the amount of time that you're down. If you want to do a little more reading into this, there's a highly published article called Oracle's Maximum Availability Architecture, and it's often referenced. But what do we take away from this is that the more replication that we have, the more availability we have. But I will say this, costs multiply quickly. Every time we add a new component, we're multiplying our infrastructure costs immediately. So let's start off with the basics. What is basic active architecture? Well, basic active architecture is kind of like what my apartment is. I have a tiny little apartment. I have my fiance and I have my cat. And if we have dirty dishes on our stovetop, we can't cook. If we want to cook, we've got to get rid of those dirty dishes, go clean them up, and then we can finally make something on the stove. And that's kind of what basic active architecture is. We have our web layer, our application layer, or service layer, and we have our data layer, whether that's a data store, document store, or a database. Now, this is good for some applications, but it very often is not nearly enough. But what it is good at is being cheap, being simple, and being fast to market. Sometimes you need these things for maybe a POC or MVP, and that's what you're going for right off the bat. But if this is in production and something fails, you're going to have lots of manual intervention whenever you fail over. You have a very low level of resiliency because you have downstream dependencies, but nothing increasing your availability. And later down the line, if you're looking to scale this, looking to add more customers, hoping to always be on, you're going to need a lot of rework. Some examples of this would be internal tools that, if they went down, could possibly be inconvenient, but it's often not enough. So what's next? Active-passive architecture. And to use another cooking example, I don't know how many grandmas are like mine, but my grandma has 2 freezers, completely separate. One's outside, one's inside. And when I asked her why, she said that whenever one breaks, she has another one. And I said, oh, okay. So basic active-passive architecture kind of looks something like this. We have our set of applications or components in one region, region A. We have our main database or our master database in region A, and we have a read replica as well as one web and one app in a second failover region. Whenever something fails, we move everything to our region B. When we want to begin bringing everything back over to our original region, we instantiate another read replica, fail everything back over, and we bring up a new read replica. Now, these passive components that you see that are light-colored, there are often 2 versions of it. You can either have a hot or a cold standby. With hot standbys, you have instances with code, but they're not taking any traffic. And when you have a cold standby, you have automated failover scripts that you have planned for. At this level, we have statelessness that comes into play. Whenever you do fail over to that other region, it's absolutely critical that anything running in your second region is going to produce the exact same results as if you were running it in your original region. So what is it good for? We are heavily decreasing downstream dependency, decreasing downtimes. And we also have a set of backup services. So this is at this level where we have backups for our data, and we also have backups for our services. So we increasing availability and increasing durability. It's often a very good balance for most applications, but at this level, we begin increasing cost and complexity, and we also have that potential for data loss whenever you fail over from one region to the next. Your recovery time is going to look at whatever your the amount of time that it takes to start up your new set of servers, but for most applications, this is where you're going to want to fall because it's a good balance between cost and complexity and availability and durability. This is good for low-revenue customer-facing applications, some e-commerce apps, and batch processes that can possibly make up for any lag that you may have associated that aren't mission-critical for real time, and possibly still meet your SLAs. So active-active. This is where your complexity and your costs become extremely high. In active-active, we have multiple instances of our servers taking traffic at the same time. This may either be to balance out your load, or maybe you have geological constraints that you need to. Maybe you're serving up in China as well as the US, as well as the UK, and you may need to appropriate for that latency. And depending on your data consistency, you may need region-local data stores, or you may need one source of truth. Your database and data store implementation are going to depend extremely heavily on what technologies you use. If you're public-facing, your DNS would need to know about your public IPs as well as both sets of servers. And if you're internal-facing, your application logic would need to know about both servers. So what is great about active-active? Obviously, it's always on. At least hopefully, right? We're going to minimize our data loss, and we're going to hopefully have zero intervention whenever something fails. This is where everything becomes much more expensive, much more complex, and we're going to have some limited tooling. When we get to active-active data stores or active-active services, we begin to limit ourselves in terms of what types of technologies we can use in order to write all of our transactions to. Now, this is active-active would be used often in emergency services, life-threatening services, things like airline controllers, or if you have a mission-critical application like Google's search engine, or at Capital One, we have our investing and loan payments streams. This is where active-active would come into play, where you need to take payments all day, every day. So our considerations and trade-offs are appetizers, if you will. We're going to talk a little bit about, first off, data replication. Data replication, we need to begin thinking about how durable our data is. So let's take this simple application. We have a request that goes into our app or service, and that app does some type of transaction off of our master database. And we have a read replica that's replicating off of our master database. We begin adding a lot of complexity just based off of including that read replica into our pipeline. This is very typical with this read replica and master setup. And what we need to begin considering very early off is what type of data are we replicating, and how are we replicating it, and how often we're replicating it. Maybe you have transactions or user data that you need to replicate synchronously, or maybe you have maybe if you're serving up videos or media content, that can be asynchronously replicated later down the line, and that's perfectly fine for you. Whenever we do add in our read replica, we need to consider the replication lag as well as the latency that's added per request and transaction whenever we write to our database. And we need to also consider whatever database we're using, what type of retry policy does it have? And is that going to increase the amount of latency per write? So let's kick it off with this. We have active-active data store. Now, at face value, this looks really, really good. And I think most people will agree. Avoid this. Now, when we have active-active data stores, we have obviously two master databases in sync with each other. Every time you write to one of the other databases, you're also replicating that data over to the other. But then we add the issue of what happens when you have collisions. Which database is the source of truth? Which database is auditable? And this is where we need to begin treading very carefully. Latency also becomes a very large issue here. We need to have, if you need synchronous replication, then we're going to increasing our latency and have higher potential for collisions. So right off the bat, we need to consider, can we asynchronously replicate our data? And do we really need an active-active data store? Not always. Now, in this scenario, we have both of our apps in each region writing to one single master data store. And if your DB fails, your master database fails, you can promote your read replica and have all your applications writing to your new master. And this is very critical because we are still active at the service level. We're just not active at the data level. So if you need higher availability, but you don't need strong data consistency, or you don't need high data durability, often this is good enough for you. And that's an important distinction. Whenever possible, we should be using services and resources within the region, and that's a trade-off between your availability and durability that needs to be made very early on. So some tools and services that I wanted to share with you guys that I found interesting. GCP's Cloud Spanner, Azure's Cosmos, and AWS's Aurora all offer some type of read-write replica or a multi-master global configuration that can help you with those needs, but you do need to consider the collisions up front. I will say that with Cloud Spanner, it uses a non-standard SQL driver, so if you need to re-architect, it would require non-trivial work. With Cosmos DB, it's actually pretty interesting. They support multiple data types. So you can have key value as well as a graph database or a table within your same database. And with Aurora, they have a new offering called Aurora Serverless, which you only pay for underlying costs whenever you're not writing transactions, which would heavily help you with those costs incurred whenever you increase your complexity in infrastructure levels. If you don't want to go the managed route and don't want to be tied to a cloud provider, there is Apache Cassandra and MySQL. And the reason why I want to point these guys out is because Cassandra is heavily used at Capital One, and Netflix has also stated use of Cassandra for cross-region master-master data stores. And MySQL is used for GitHub's global data store, as well as for a variety of uses from Capital One. So what happens when we do failover? So we have, in this scenario, an API that takes in traffic, and it makes a request to an app, and it sends a message to a topic, Kafka, if you will. We have multiple streams reading from that topic, and those streams are doing something to a database. Maybe they're updating, maybe they're writing, maybe they're deleting. What happens when one of your databases fails? Are we going to move one of our databases over to a new region or failing over? Are we going to move over our entire pipeline? Maybe just the stream and its associated database? Maybe all of our streams and all the databases. So it's important to consider what we're failing over, and that's the idea of tenancy. The idea of tenancy, or multi-tenancy, is a single unit of movement that you need to fail over in order to have your working pipeline once again. In general, we want to contain the blast zone as much as humanly possible. Failure in one region should not affect another region, and we should have a heavy amount of regional independence whenever we're serving up requests, either at the service level or at the data level as well. And very early on, we need to begin considering what are possible scenarios for failover and what can we automate right off the bat. When we begin looking at what can fail over and how do we recover from that, we need to begin looking at what we're monitoring. Monitoring in terms of what's healthy, what's not healthy, what we're going to fail over, and we need to ensure that the alarms are in place for whenever things do fail. Log analytics like Kibana or Splunk are extremely useful here. But as we increase availability and we increase durability, you're going to increase your complexity, and you're going to increase your cost. And all of this is important because not every team has the bandwidth or the associated costs that they want to provide whenever you increase your resiliency. Everybody wants to be active from the start, but not everybody needs to be active from the start. There's lots of upfront costs, and that can possibly provide lots of value later down the line, but that's a trade-off that needs to be considered very early on. You also need more agents here, including software engineers, SRE, product management, and they all need to be in line with whatever levels of complexity for your data and your services you can provide. So let's talk about patterns to increase your availability. First off, I do want to point out that there are hundreds, if not thousands, of different patterns to increase the availability and resiliency. These are a couple that I found particularly notable in the industry, and I wanted to share. So we have component X, which calls component Y. What happens when component Y fails? We can implement a simple retry policy, keep hitting component Y until it gets healthy, but that adds a lot of unnecessary latency and could possibly result in timeout. So the circuit breaker pattern is when we wrap a protected function call around a circuit breaker object, and whenever we reach a certain threshold of failure, we just stop calling it. In Java, I want to call out Netflix's Hystrix library, which is an amazing tool. But retries aren't necessarily bad. They just need to be done with lots of consideration. So that's where something like the exponential backoff pattern comes into play. And in a very naive manner, every time we have a failing call, we increase the amount of time before our next retry call. And something like that looks like after our first failure, we wait about 200 milliseconds. After our fourth failure, we wait 1,600 milliseconds. And after our ninth failure, we're waiting around 51 seconds. And this allows us to continue retrying, but it allows the failing system to recover, and it gives it more time to recover and become healthy. But in the meantime, while our dependencies are down, you're probably asking, well, what do we do then? We have a fallback pattern. Do you guys remember Waffles? I hope you do. He's really cute. Fallback pattern is when we return a stubbed response. That may be by way of having cute images on your 404 page, or that might be a way of returning data stored in a cache. And in terms of cache, nothing comes close to Memcached and Redis. There are many managed caches out there that can heavily help you out. AWS has Elasticache, GCP has Cloud Memory Store, and Azure has its Redis cache. And the great thing about these managed services is that you don't have to maintain or patch your infrastructure. Now, for the next pattern, I do want to call out one company, which is pretty inspiring, Netflix. In a very naive manner, we have a web, stream, and database. And if you don't know what Netflix is, they stream videos for us so that we can watch unhealthily. Now, in 2012 or 2013, their ELB plane that they were using failed. And it was completely outside their control. And what that means is everybody on the East Coast of the Americas could not watch Buddy the Elf or A Christmas Story or whatever you're into on Christmas Eve. And that's completely tragic, because I do love watching Buddy the Elf on Christmas Eve. So what they did in a very simple representation was they looked at what happened when that region failed and how we can prevent that one region, how we can prevent failures whenever that one region does fail. So they said, why don't we have a set of instances running, multiple instances running within our region, and we separate it via availability zones. So whenever one availability zone goes out, we can still serve up traffic from our other availability zones that are still healthy. And that's awesome, because most people automatically jump to cross-region active-active right off the bat. Whenever you say, oh, we need active-active, let's do cross-region, let's do East-West and Australia. That doesn't necessarily need to be the case. They're active-active within their region. They're keeping network latency to a minimum, and they're keeping their services calling within the same region, and that's awesome. So they're also increasing their overall availability via horizontal scaling by adding multiple copies of those instances within their same region. Another one I want to call out is asynchronicity. And over the years, the past couple of years, asynchronous and event-based notifications and driven events have become extremely popular by ways of RabbitMQ or Kafka. And a lot of people, some people think that, oh, we're using this to maybe just have batch processes, but it also immediately adds to your resiliency levels. Why? Because we're decoupling components. In this scenario, we have our app which writes to a topic, and it gets to fire and forget that message. Once it's done, the app doesn't need to know anything else. It lets the message sit inside of its topic until any worker queues or any workers need to pull that message off. Messages can sit in the queue until they're ready to be processed. And asynchronicity alleviates a lot of that unnecessary waiting on the application's or the producer's part. We're also reducing reducing the chance of cascading failures and timeouts, and we're also reducing the network congestion associated with the app waiting on worker queues to do its job. Unfortunately, using worker queues, streams, and asynchronous design isn't always the most straightforward, and that needs to be looked at very carefully. And if the original producer does need to look at the results somehow, you do need to keep track of some type of job ID. This also adds directly to infrastructure costs and complexity, but it is overall a very powerful tool to minimize the effects of failure on your system. So in terms of tools that we can use, Kafka is very widely used in a lot of spaces, developed at LinkedIn, and it's now open source. One of the big things Kafka sells as an open source tool is its extremely high availability and throughput. It also offers multi-node and multi-cluster configurations, and your messages can sit in your queues, and if you need to, you can reread your messages whenever you need to, as you can dedupe later. Kafka follows a smart consumer and dumb broker model, which is the exact opposite of what RabbitMQ has to offer. They follow a smart broker and dumb consumer model, which means that you can develop very complex topological schemes for routing your messages. RabbitMQ does support multiple types of protocols if that's something you need, and then they have very well-defined consistency rules. Oh, and another thing I do want to mention that not every shop has the capacity to manage a Kafka or RabbitMQ cluster. In way of managed services, you have Google PubSub, SQS, Kinesis, and things like that if you want a managed service. But you don't always have to take one of these patterns and deploy it. You can combine patterns, combining asynchronicity, queues, and worker streams, and maybe the exponential backoff method become extremely powerful whenever you need to increase your resiliency heavily. Two more tools and services I do want to mention are Chaos Monkey. If you're unfamiliar with Chaos Monkey, it is developed at Netflix. It's used to randomly terminate instances inside of your environment, and at first that sounds really, really scary. And it also sounds like, oh, do I have to deal with failure once a day? In general, it's used to schedule your downtime so that you can practice what happens during a real failover. Netflix famously runs this in their production environment on a daily basis. So take that with what you will. And the last thing I want to talk about before we go is serverless. Serverless is a very, very hot topic right now, and it's brought up in conversation a lot. If you're unsure what it is essentially a function as a service. You're putting in a small bit of code, and you're waiting on events to happen on services inside of your cloud provider to kick off this function. All of the following have issues with debugging, monitoring, and deployment, as well as version management. But the one thing that it does provide that is reducing costs dramatically. In general, functions don't run whenever you're not utilizing it, and they do go down or go dark. And it does encourage stateless programming, going back to before, whenever we want to deploy to multiple regions or multiple availability zones, we want to make sure that we get the same output no matter which region we're running in. So as with every talk, we've only hit we're only touching on the tip of the iceberg. We talked about like planning early and statelessness and having a plan whenever you fail over, but this is just the very beginning. Resiliency is a very deep topic that requires lots and lots of time and effort, and everybody's solution is going to be different because everybody's business requirement is going to be different. And that's where the fun begins. It's when you begin architecting for your project. My name is Stephen Dang. Thank you.